Good morning, students. Welcome back to session 7 of vector spaces class. In this class, we'll study inner product spaces and results related to inner product spaces. Okay. Generally, vector spaces are defined over arbitrary field. Okay. Arbitrary field F. Okay. In this section, so we restrict F, the field F, to the only field of real or complex numbers. To the field of real or complex number. That means F is either R or C. Okay. So first we'll define what's meant by an inner product space. Okay. Let V be a vector space over a field F. F is, as I said, it is either R or C, either set of real space of real numbers or complex numbers. Then a map denoted by this symbol from V cross V to F, which assigns for every pair of elements U comma V in V a scalar denoted by this inner product of U comma V in F is called inner product. Means a map, this is like F, which is mapped from V cross V to F, which gives for every pair of elements say U comma V, F of U comma V is a scalar in F. That scalar either a real or a complex. Okay. So that is denoted by this symbol called the inner product. It is just a function. Okay. Now, so this is called inner product if the following conditions are satisfied. Inner product of U comma V is equal to V comma U conjugate. Okay. So inner product is so U comma V is V comma U conjugate, complex conjugate. If F is real, what will happen? V comma U, U comma V is same as V comma U, because V comma U conjugate of a real number is itself. Okay. Next, second condition is inner product of U comma V is non-negative, and inner product of U comma U is 0 if and only if U itself is 0. Okay. And the third condition is inner product of alpha U plus beta V comma W is alpha into U comma W plus beta into V comma W. Okay. So this holds for every vectors U, V, W belongs to V, and alpha and beta are scalars here. So the map which maps from V cross V to F, which satisfies these three conditions, is known as the inner product on V. And the space, vector space V together with this inner product is known as the inner product space. Is known as the inner product space and is denoted by the symbol pair V comma this. Okay. We can specify by this symbol, or simply we can say V is an inner product, means it is understood that V contains a inner product. Okay. So now let's come to this. If F is the field of real numbers, then the inner product of U comma alpha V plus beta W is equal to what? If it is on the right hand side, so this is equal to alpha into U comma V plus beta into U comma W, because look here, inner product of U comma alpha V, U comma alpha V plus beta W. So this is equal to what? By definition, this is inner product of alpha V plus beta W comma U conjugate. Right? This you know. So if I take this, use the linearity condition, it becomes alpha bar in alpha bar. This is alpha bar into inner product of V comma U bar, right? Plus beta bar into inner product of W comma U conjugate. Okay. So this is equal to, this is alpha bar into inner product of V comma U conjugate, means what? U comma V. Okay. Plus beta bar into inner product of U comma W. Therefore inner product of U comma alpha V plus beta W is what? Alpha bar into U comma V plus beta bar into U comma W. U comma W, right? So now if f is r, what will happen? Alpha bar is alpha into u comma v plus beta into u comma w if f is what? R. Okay, and if f is complex, then this is equal to inner product of u comma alpha v plus beta w is alpha bar into u comma v plus beta bar into u comma w. Beta bar into u comma w. Okay. Next, let us take up some examples for this inner product space. So among them, the first example, I'll take, let f be any field and let v be the set of all n tuples of elements of f. V be the set of all n tuples of elements of f. That is what? V is equal to fn. I will denote. F is the field of complex number. Here particular f is the field of complex numbers. So define for the elements u and v in V, means if u belongs to V, then it is the n tuple of complex numbers alpha 1, alpha 2, etc. alpha n. If v belongs to V, means it is the n tuple of complex numbers beta 1, beta 2, etc. beta n. Each alpha I and beta I are the elements of f. Okay. Now you consider the inner product. Inner product of u comma v is equal to, I will define like summation I is equal to 1 to n alpha I into beta I bar. Okay, summation I is equal to 1 to n alpha I into beta I bar, or in other words, if you split at this, so alpha 1 into beta 1 bar plus alpha 2 into beta 2 bar, etc. alpha n into beta n bar. If we define an inner product like this, then what will happen? Then uv defines an inner product on V and V becomes a inner product space. Okay, we can verify the properties of a inner product space, inner product using this one, this function. Okay. Next is, this is like a different example. Say let V denotes the set of all continuous complex valued functions defined on 0, 1. Such type of sets, you know, V is the set of all continuous real valued functions defined on the interval 0, 1 you have studied. It is the complex valued functions. That is, V is equal to set of all f such that f is a function from 0, 1 to c which are continuous. Now for any two elements f and g in V, for any two elements f and g in V, we define the inner product of f comma g is equal to integral from 0 to 1 f of t into g of t bar into dt. So I define the integral inner product of f comma g is equal to integral from 0 to 1 f of t into g of t bar into dt. This is g of t bar means complex conjugate of g of t. Then definitely again this defines an inner product on V, and V together with this inner product is a inner product space. Okay, V together with this inner product is a inner product space. So let us take up some fundamental results in this now. Okay, say suppose V is an inner product space, then what will happen? Inner product of 0 comma V is equal to 0 for every vector V belongs to V implies this itself is 0. Okay, means inner product of 0 comma V is 0, always 0 for every V belongs to V. Okay, inner product of u comma V is equal to 0. Inner product of u comma V is 0 for every V belongs to V implies what? U must be 0. These are very simple. Say now first one, inner product of 0 comma V can be written as 0 into 0 comma V. 0 scalar can be taken out by the definition of inner product. 0 into 0 comma V is 0 into multiple of anything is 0. Therefore inner product of 0 comma V is 0 for every V belongs to V. So likewise 0 comma V or V comma 0 itself is always 0. Okay, because 0 comma V is equal to V comma 0 conjugate, that is equal to 0 conjugate. 0 conjugate of 0 is 0 itself. Okay, second, given inner product of u comma V is 0. Now inner product of u comma V is 0 for every V belongs to V. Now u is also an element of, okay, u is also an element of V. Therefore if we take V is equal to u, here what do you get? Inner product of u comma u is 0, which implies u is equal to 0. Okay. Next we will take another problem. Suppose W1 and W2 are subspaces of a vector space V. If W1 and W2 are inner product spaces, then W1 plus W2 is also an inner product space. Means sum of any two inner product spaces is again an inner product space. For this, let x comma y belongs to W1 plus W2. Then how x looks? X is u1 plus u2, where u1 is an element of w1, u2 is an element of w2. Again, y belongs to w1 plus w2 implies y is equal to v1 plus v2, where v1 is an element of w1, v2 is an element of w2. That is, u1, v1 are elements of w1, u2, v2 are elements of w2. Now define an inner product on this w1 plus w2 by inner product of x comma y. Inner product of the elements x comma y is what? Inner product of u1 plus u2 comma v1 plus v2. That I have defined it by, so u1 comma v1 plus u2 comma v2. Okay. So inner product of xy is inner product of u1 plus u2 comma v1 plus v2 is u1 comma v1 plus u2 comma v2. Now I will prove this is an inner product on w1 plus w2. So consider inner product of yx bar. Inner product of yx bar is what? This is yx is what according to this? v1 comma u1, v1 comma u1 plus v2 comma u2 whole conjugate. But we know that z1 plus z2 conjugate is z1 conjugate plus z2 conjugate from complex analysis. So this can be written as v1 comma u1 conjugate plus v2 comma u2 conjugate. So now this is equal to, if you remove the conjugate, it becomes u1 comma v1 plus u2 comma v2. So this is nothing but what? The defined inner product x comma y. Therefore xy is equal to yx bar. First condition we have proved. Let's come to the second. Now clearly inner product of x comma x is u1 comma u1 plus u2 comma u2 by definition. Definitely u1 comma u1 is always non-negative because it is an inner product in w1 and w1 is a inner product space, and u2 comma u2 definitely is greater than or equal to 0 because this is an element of u2 is an element of w2. So inner product w2 is a inner product space. Therefore u2 comma u2 is non-negative. Therefore sum of two non-negative numbers is non-negative. Therefore x comma x is non-negative for x belongs to w1 plus w2. And x comma x is 0. Inner product of x comma x is 0 happens if and only if what will happen? This is u1 comma u1 is 0, u2 comma u2 is 0. Now u1 comma u1 is 0 by definition, u1 is 0, u2 comma u2 is 0 means u2 is 0. Therefore x itself is 0 because u1 u2 are zeros means x itself is 0. Okay, we have proved the second condition. Let's come to the third one. Inner product of alpha x plus beta y comma z. So this again by using the above property we can clearly show that this is equal to alpha into x comma z plus beta into y comma z for every x y z belongs to w1 plus w2 and alpha comma beta belongs to f. This we can easily verify. Therefore the inner product what we define is an inner product on w1 plus w2, and so w1 plus w2 is an inner product space. Okay, w1 plus w2 is an inner product space. Now you know this definition. Say let V be an inner product space. Then for the element V in V, the norm of V or the length of V is denoted by this symbol. This is called the norm. Okay, norm of V, and is defined as norm of V is equal to inner product of V comma V under root or V comma V to the power of 1 over 2. Okay, V comma V to the power of 1 over 2 for every V belongs to V. So norm of v denotes the length of the vector. Okay, length of the vector. Norm of say u minus v denotes the distance between u and v. Okay. Here for the norm of alpha into u is equal to mod of alpha into norm of u, where alpha is any scalar. For this you consider norm of alpha into u whole square. Norm of alpha into u whole square is what? Alpha u comma alpha u, because norm of v square is what? V comma v. Therefore you apply the property, you take alpha into u comma alpha u. Now alpha is in the second component, so if you come outside it will come with a complex conjugate. Therefore alpha bar into u comma u. Therefore alpha into alpha bar is what? Mod alpha square is equal to mod alpha square into u comma u, inner product of u comma u. That's equal to mod alpha square into u comma u, again can be written as norm of u whole square. Thus norm of alpha u square is mod alpha square into norm of u square, or we can declare that norm of alpha u is equal to mod of alpha into norm of u for every element u belongs to v. Okay. Now, so we proved the squares inequality, which is one of the important inequality in the inner product space. This squares inequality says if u and v are any two elements of inner product space V, then mod of inner product of u comma v is less than or equal to norm of u into norm of v, or absolute value of inner product of u comma v is less than or equal to norm of u into norm of v. Now say if u or v is 0, one of u or v is 0, then what will happen? Inner product of u comma v is 0, because inner product of 0 comma v is 0, or u comma 0 is also 0, and for the 0 vector norm of 0 is 0, or norm of u is 0 or norm of v is 0 according to u is 0 or v is 0. Therefore we get norm of u into norm of v is 0, and this is also 0. Therefore the result is true when u or v is 0. Okay, so let u is not 0 and v is also not 0, and in the first case suppose the inner product is real, u comma v is real. What will happen? Let's see. Okay, now consider inner product of lambda u plus v comma lambda u plus v. Now u and v are elements of v means lambda u is an element of v, and v is an element of v means lambda u plus v is an element of v. Okay, therefore we can consider such elements. Now norm of any element is always non-negative, so I taken greater than or equal to 0. So this will be equal to, I will use lambda into u comma lambda u plus v plus v comma lambda u plus v. Okay, that's equal to lambda into, okay, since the inner product is real, I can write u comma v as v comma u. So I written lambda into lambda u plus v, first term write like this, comma u plus again lambda u plus v comma v, right. So this is equal to, lambda can be taken out, lambda into lambda u comma u comma u, lambda plus lambda into v comma u plus again lambda into u comma v plus inner product of v comma v. So this is equal to what? Lambda square into u comma u plus 2 times lambda into u comma v, because v comma u same as u comma v, because inner product is real. Okay, plus 2 lambda into u comma v plus inner product of v comma v. Okay, understand this, lambda square into u comma u plus 2 lambda times into u comma v plus v comma v. Okay, so now I will take this is equal to, I will multiply and divide throughout by u comma u, inner product of u comma u. What will happen? This is equal to, okay, 1 over inner product of u comma u as it is, I multiply throughout by inner product of u comma u, that becomes lambda square into u comma u whole square plus 2 lambda into u comma v, already it is there, plus u comma u into v comma v. So this is equal to 1 over u comma u into, I will write this as lambda times u comma u plus u comma v whole square. This becomes what? Lambda square into u comma u square plus 2 lambda times into u comma u comma v, and the third term is u comma v whole square that I subtracted here, minus u comma v whole square. Okay, so I'll split the above term into two terms, like plus 1 over u comma u into u comma u v comma v, this is already there, minus the term u comma v whole square. So this is equal to, now these two terms are non-negative because the left hand side is non-negative, means each of the terms must be non-negative. Therefore 1 over u comma u into this term u comma u v comma v minus u comma v whole square is non-negative. This implies what? U comma is definitely non-negative, so this is equal, this implies u comma v whole square. If we transform this term to right hand side, u comma v whole square is less than or equal to u comma u into v comma v, or this implies mod of u comma v whole square is less than or equal to, now this can be written as, okay, this can be written as, look here, square I removed, so it will be inner product of u comma u whole to power of v comma v whole to power of. Okay, because if you want, you can take the, you can say that it is, we have taken the root, square root on both sides. Okay, so and this is the term. Okay, now because you know that x is always less than or equal to mod x, x is always less than or equal to mod x, so I use this term here. Okay, so this is equal to what by definition? Norm of u into norm of v. Thus mod of inner product of u comma v is less than or equal to norm of u into norm of v for every uv belongs to v. Therefore squares inequality is proved for the inner product space which is real. Now let us take up the inner product which is complex. Suppose u is not 0, v is not 0, and inner product of u comma v is complex. Then consider the inner product of u comma u by inner product of u comma v. So this is equal to, it is like a scalar, inner product, it is a scalar that I can take it outside of this inner product. So 1 over inner product of u comma v into inner product of u comma v. So what it gives? It gives 1. 1 is a real quantity. So this total term is a real quantity. The total term is a real quantity means what? We have proved the result for squares inequality for real numbers. Therefore this becomes 1 is equal to u by inner product of u comma v, that is 1. Okay, which is less than or equal to, because as I said, mod z is always less than or equal to mod z, so apply mod of this above term. But this is, since this is a real number, as I said, it is a real number, therefore I can apply the above case 1 which is real. So this is less than or equal to what? Norm of, this is like u and this is v, norm of u into norm of v. Therefore this is equal, less than or equal to u by inner product of u comma v under norm into norm of v. Okay, so it is again, it is like norm of alpha into u is what? Mod of alpha into norm of u. So this is mod of alpha means 1 by mod of inner product of u comma v into norm u on the numerator, I written as it is, into norm of v. So if I send this term denominator to left hand side, what will get? Left hand side is 1, so it will be multiplied with 1 gives mod of or absolute value of inner product of u comma v is less than or equal to norm of u into norm of v. Thus we have proved the squares inequality for both the cases when the inner product is the real case and the inner product is complex. Okay. Next, suppose you have a remark here. The above inequality means inequality, the squares inequality will become equality if and only if u and v are linearly dependent. Okay, so not independent, linearly dependent. So the above inequality are we have a equality in squares inequality if u and v are linearly dependent. So suppose u and v are linearly dependent. U and v are linearly dependent means what? One is a multiple of the other. One is a scalar multiple of the other. That means we will take u be a multiple of v. Say u is equal to alpha into v, where alpha is a scalar. Then what will happen? Inner product of u comma v is equal to, under absolute symbol, absolute value symbol, so or mod symbol, that is mod of inner product of alpha v, because u is alpha v comma v, that's equal to mod of alpha into inner product of v comma v. So that is equal to mod of alpha into v comma v is what? Norm of v square. Okay. Similarly, norm, this is the left hand side. Similarly, norm of u into norm of v is norm of alpha v, norm of alpha v into norm of v, that's equal to mod of alpha into norm of v into norm of v. Okay. So this becomes mod of alpha into norm of v whole square. Therefore, inner product of u comma v under mod sign is also mod of alpha into norm of v square, and inner product of u and norm of u into norm of v is mod of alpha into norm of v square. Therefore, these are right hand side of the above expressions are same, means the left hand side must be the same. Left hand side must be the same means mod of inner product of u comma v is equal to norm of u into norm of u, because this is the equality case of squares inequality. Okay. This happens if and only if u and v are linearly dependent. U and v are linearly dependent. Okay. Now, say let us take up the other definition. Say suppose V is a inner product space, and suppose u and v are any two elements of V. We say u is orthogonal to V. U is orthogonal or perpendicular to V. We say u is orthogonal or perpendicular to V if inner product of u comma v is 0. If the inner product of u comma v is 0, then we say u is orthogonal to v. Also, inner product of u comma v is 0 means inner v comma u is what? U comma v bar, that is 0 bar is 0, means if u is orthogonal to v, then v is also orthogonal to u. You know that u is orthogonal to v means certainly v is also orthogonal to u, geometrically if we see. Okay, orthogonal means perpendicularity. If u is perpendicular to v, definitely v is perpendicular to u. So we say this is the case. Now suppose we have n number of vectors u1, u2, etc. un of vectors in v. Then when you say these n vectors are orthogonal to each other, if these are orthogonal to each other, if inner product of ui comma uj is 0 whenever I is not equal to j, means u1 comma u2 is 0, u2 comma u3, for every pair of elements when I is not equal to j, ui comma uj is 0. Then we say the set of vectors in a inner product space are orthogonal vectors. Now let's come to this definition. The set of vectors, the same set of vectors u1, u2, etc. in a inner product space V, the set is said to be an orthonormal set. The above set is said to be an orthonormal set if each of the elements or each of the vectors in this set have length 1. Each of the elements in this set have length 1, that is norm of ui is 1 for each I, or inner product of ui comma ui is 1 for each I, and for I is not equal to j, inner product of ui comma uj is 0. That to say this is the above set is orthogonal set, this is orthonormal set. Orthonormal set of vectors are those vectors which are orthogonal as well as they have unit length. Okay, orthonormal set of vectors are the vectors which are orthogonal as well as their length is 1. Okay, so combining this statement, these two statements, we can say that the set of vectors u1, u2, etc. un in a inner product space V is said to be orthonormal set if inner product of ui comma uj is 1 if I is equal to j and 0 if I is not equal to j. Okay, ui comma uj is, inner product of ui comma uj is 1 if I is equal to j and 0 if I is not equal to j. Then we say this set is an orthonormal set. Okay. Now say let W be any subspace of a inner product space V. Then the orthogonal complement of W written by W perpendicular, or call it as W perp perpendicular. Okay, written W perp is defined as W perp is equal to set of all x belongs to V such that inner product of x comma y is 0 for every y belongs to W. This is very important definition. W perp contains those vectors of V only such that those vectors which are orthogonal to every vector of W, okay, means which are perpendicular to every vector of W. Now can W perp is empty? No, because we have 0 element belongs to V. 0 comma y is 0 for every y belongs to W, therefore 0 belongs to W perp. But 0 is also in W because W is a subspace, right? Therefore 0 is the only vector which lies in both W as well as W perp. Therefore we can say 0 belongs to W intersection W perp. Okay, and in fact we can show that this orthogonal complement W perp is a subspace of V. From this definition you can see that this is a subset of V, but we can show that W perp is itself is a subspace of V if W is a subspace of V. For this, showing this is very easy, simple. Let x1 and x2 be any two elements of W perp, be arbitrary, and alpha comma beta be scalars. Then for all y belongs to W, then for all y belongs to W, we have inner product of alpha x plus beta alpha x1 plus beta x2 comma y is equal to what will happen? Alpha times inner product of x1 comma y plus beta times inner product of x2 comma y. But x1 belongs to W perp means x1 comma y is 0 for every y, and similarly x2 comma y is 0 for every y belongs to W. Therefore alpha into 0 plus beta into 0, that's equal to 0, means inner product of alpha x1 plus beta x2 comma y is 0 for every y belongs to W, implies alpha x1 plus beta x2 belongs to where? It is in W perp. Therefore alpha x1 plus beta x belongs to W perp implies W perp is a subspace of V. If W is a subspace of V, then its orthogonal complement W perp is also a subspace of V. Okay, already I said 0 is the only vector which is common to W intersection W perp. If you want to show this, you choose some vector x belongs to W intersection W perp, then x belongs to W as well as x belongs to W perp. Now x belongs to W perp implies what? Inner product of x comma y is 0 for every y belongs to W. Okay. Now x is also element of W, therefore in particular for x belongs to W, inner product of x comma x is 0. If inner product of x comma x is 0, then by definition of an inner product, x itself is 0. Thus we have considered some x is in W intersection W perp and that x itself is 0, means every element in W intersection W perp is 0, that is W intersection W perp contains 0 only. Okay. So next let us take up the other result, which states if V is an inner product space, then first one, norm of x plus y is less than or equal to norm of x plus norm of y for every xy belongs to V. This inequality is known as triangle inequality. Okay, and the second one is norm of x plus y whole square plus norm of x minus y whole square is equal to 2 times norm of x square plus norm of y square. This is called the, this you know from geometrically, this condition is nothing but the parallelogram law, because it denotes the squares of the sum of the diagonals of a parallelogram is equal to 2 times the squares of their sides, and also it is such that the length of the third side of a triangle is less than or equal to sum of the lengths of the other two sides. Okay, so that's why it's called triangle inequality, and the second one is called parallelogram law. They are very simple, only the computation Okay, so first one is norm of x plus y square is what? Inner product of x plus y comma x plus y. So I use the x comma x plus y plus y comma x plus y, that's equal to x comma x plus x comma y. Next is y comma x plus y comma y. So this is equal to norm of x square plus this is norm of y square plus xy. This yx can be written as xy bar. Now z plus z bar. What is z plus z bar? If z is equal to x plus iy, look here, if z is equal to, say z is x plus iy and z bar is what? It becomes x minus iy. Therefore z plus z bar gives what? Z plus z bar gives 2x, means this can be written as 2 times real of z, right? So that property we have used. So this is equal to 2 times z plus z bar, that is 2 times real of x, z, 2 times real of z, z is x inner product of x comma y. So this is less than or equal to norm of x square plus norm of y square plus 2 times. Now you know that norm of 2 times norm of real of real of x comma y is less than or equal to 2 times as it is mod of x comma y whole square. Mod of x comma y whole square, because mod of z means what? X square plus y square. Definitely x is less than or equal to this one. Okay, this x is less than or equal to x square plus y square. Okay, so this is less than or equal to norm of x square plus norm of y square plus this is can be written as by squares inequality 2 times norm of x square plus norm of y square. So it is the like x plus y whole square formula. So norm of x plus norm of y whole square. Therefore what you can say, norm of x plus y whole square is this much. Therefore norm of x plus y is less than or equal to norm of x plus norm of y. So we have proved the triangle inequality. Let's come to the second one. Okay, norm of x plus y whole square plus norm of x minus y whole square is what? Norm of x plus y whole square is inner product of x plus y comma x plus y. The next is norm of x minus y whole square is inner product of x minus y comma x minus y. So this is by computation we can see that this is norm of x square, norm of y square plus inner product of x comma y plus inner product of y comma x. First is. The second is norm of x square plus norm of y square minus inner product of xy minus inner product of yx. So these two get cancelled. This gives 2 times norm of x square plus 2 times norm of y square. So 2 can be taken out. So this is sum of norm of x square plus norm of y square. Okay. So norm of x plus y whole square plus norm of x minus y whole square is 2 times norm of x square plus norm of y square. This is the parallelogram law. Okay. Next is the other equality is Pythagorean theorem. This is the Pythagoras theorem, like say it is let V be an inner product space and xy belongs to V such that x is orthogonal to y. Suppose x and y are vectors in V such that x is orthogonal to y, then norm of x plus y square is norm of x square plus norm of y square. Because see here, if x is orthogonal to y, then what will happen? Inner product of xy is 0. If inner product of xy is 0, then inner product of yx is also 0. Therefore, norm of x plus y whole square is equal to what? Norm of x square plus norm of y square plus inner product of x comma y plus inner product of y comma x. This already know. So these two becomes zeros. So this is equal to norm of x square plus norm of y square. So norm of x plus y whole square is equal to norm of x square plus norm of y square. Okay. So now we will take up one important lemma. This lemma says an orthonormal set of vectors in an inner product space are linearly independent. Means if the vectors are orthonormal, then they becomes linearly independent. Okay. So let v1, v2, etc. vn be an orthonormal set of vectors in an inner product space V. And consider the linear combination of these vectors that will be equal to 0. That is, suppose alpha 1 v1, alpha 2 v2, etc. alpha n vn is equal to 0, where alpha is our scalars. Now You take the above expression, you take the inner product of the above expression with some vector, say vi. Then what will happen? This is equal to, this expression is 0, we have assumed. So 0 comma vi is 0 for I is equal to 1 to n. So the left hand side becomes then, so this is alpha 1 times v1 comma vi plus alpha 2 times v2 comma vi, and so on. In the middle term alpha is there, so plus alpha into vi comma vi plus and so on. The last term is alpha n into vn comma vi. Since the vectors v1, v2 etc. vn are orthonormal, inner product of, so any vector with vi is 0 except the vi. So all other v1 comma vi, v2 comma vi up to vn comma vi, they are all zeros except vi comma vi. Vi comma vi is what? 1, because they are orthonormal. So this implies that alpha is equal to 0. Now inner product of the above expression with vi is alpha is 0 means inner product of the above expression with v1 is 0, inner product of the expression with v2, then also alpha 2 is 0, therefore each alpha is must be 0. Each alpha is must be 0 means what you can say? v1, v2 etc. vn are linearly independent, or the set v1, v2 etc. vn is a linearly independent set. Okay, is linearly independent set means orthonormal set of vectors in a inner product space V is linearly independent. Okay, now so if the orthonormal set of vectors are linearly independent, can they be made into a basis of an inner product space V? Yes, that is answered by this famous theorem known as, this answered by this famous theorem known as Gram-Schmidt orthogonalization. So the method is adopted here is called the Gram-Schmidt orthogonalization process. Here what we do is here we can make the ordinary basis elements of a vector space to orthonormal basis. So given, suppose V is a inner product space means V is a vector space, and you know that every vector space has a basis. So that basis may be converted to orthonormal basis. That's why it is called Gram-Schmidt orthogonalization process. Okay, so it may be stated in theorem like every finite dimensional inner product space has an orthonormal basis. Every finite dimensional inner product space has an orthonormal basis means, so you know that every finite dimensional vector space has a basis. So I use those bases to make into orthonormal basis. In fact, every inner product space has a orthonormal basis, because you know that every vector space has a basis whether it is finite or infinite. Okay, here let V be the inner product space with dimension n. Let V dimension of V is equal to n. Then V is a inner product space means it is a vector space and it is of dimension n. Therefore it has a n number of basis elements. I will choose u1, u2 etc. un be a basis of V. They are the ordinary basis elements. So from these ordinary basis elements I will construct an orthonormal set v1, v2 etc. vn. Okay, so just now we have proved in the theorem that every orthonormal vectors are linearly independent. Then this set of vectors v1, v2 etc. vn becomes linearly independent. But the number of elements here are n and the dimension of the vector space is n. Therefore this set itself forms a basis. Therefore what you can say, this is an orthonormal basis. Understand now? So from the ordinary basis elements I will construct an orthonormal set having n elements which are linearly independent by the previous theorem. If they are linearly independent, as dimension of V is n, then any, we have proved that theorem also. If the dimension of V is n, then any n terms of vectors, linearly independent vectors can be make into a basis. So this becomes a basis of V called the orthonormal basis. Suppose the process is like this. This is also a very simple process. Suppose some vector w1 as u1, the given u1. Set w1 as u1 and the required vector v1 is equal to w1 by norm of W1. Okay. Then what is norm of V1? Norm of V1 becomes norm of W1 by norm of W1. It becomes 1. Therefore, norm of V1 is 1. Okay. It is a unit vector, and also single non-zero vector is always linearly independent. Therefore, the single vector V1 is an orthonormal set. Now set V2. Set the next condition is vector we obtained like this. So set W2 is equal to, okay, W2 is equal to V2, U2 already given vector. W2 is equal to U2 minus inner product of U2 comma V1 into V1. So V1 we have obtained in the step 1, and V2 is norm of W2 by norm of W2. Again norm of V2 becomes 1. Okay, and we can see that if you construct like this, then inner product of V2 comma V1. V2 is what? W2 by norm of W2 comma V1. So this is a norm of W2 is a scalar, that can be taken out 1 by norm of W2 into W2 comma V1. So 1 by norm of W2. What is W2? W2 is, I written U2 minus inner product of U2 comma V1 into V1. Okay. So 1 by norm of W2 you can take out. So you split this inner product. This becomes inner product of U2 comma V1 minus, this is scalar that can be taken out, inner product of U2 comma V1, it is like alpha, we have taken out. The other is V1 comma V1, inner product of V1 comma V1. So this is equal to 1 over norm of W2 into U2 comma V1. V1 comma V1 is what? Because norm of V1 is 1. So V1 comma V1 is 1. Therefore U2 comma V1. U2 comma V1 minus U2 comma V1 means 0. So for this is 0 means inner product of V1 comma V2 is 0. Therefore V1 V2 is an orthonormal set by definition. So we have constructed two vectors, V1 and V2, using the two vectors, two basis elements U1 comma U2. Similarly, for I is equal to 1 to n, set the vector Wi as, look here, ui they were given, ui minus inner product of ui comma v1 into v1 minus ui comma v2 into v2 etc. minus the last term is what? Ui comma vi minus 1 into vi minus 1. Okay, and vi is wi by norm of wi, then norm of vi becomes 1 for each I is equal to 1 to n. And let us take up this one, inner product of vi comma any vector, say vk. Inner product of vi comma vk is what? Vi means wi by norm of wi comma vk. This is equal to 1 over norm of wi, it can be taken out into inner product of, you write the value of wi here, you take inner product with vk. So ui minus ui comma v1 into v1 and so on. The last term is ui comma vi minus 1 into vi minus 1 comma vk. You take all the elements with inner product with vk. So it gives 1 by norm of wi into, first one is ui comma vk, I written as it is, minus, this is the scalar ui comma v1 as it is taken out, inner product of v1 comma vk. Second, likewise, so all the elements you get, the last term is what? Ui comma vi minus 1 is a scalar, it can be taken out into inner product of vi minus 1 comma vk. So this is equal to 1 over norm of wi into ui comma vk as it is, minus, you can see that inner product of v1 v2 etc. they are all up to vi minus 1 are all orthonormal vectors. Therefore v1 comma vk, v2 comma vk, they are all becomes zeros except what? The last elements vk comma vk. So this is ui comma vk, vk comma vk. So this becomes 1 over norm of wi into ui comma vk minus ui comma vk. So that is 0 for k not equal to I. You may take v1 comma vi comma v1, you can take vi comma v2 you can take. So every element is, that becomes 0 for k not equal to I. Thus, we have constructed an orthonormal set V1, V2, etc. which forms a basis. Okay. So, from the ordinary set of basis elements of an inner product space, we have constructed the orthonormal basis. The process is here the Gram-Schmidt orthogonalization process. Okay. Let us take up the example to construct the orthonormal basis. Okay. So, here I will take V to be the inner product space containing set of all functions fx belongs to f of x such that degree of f of x is less than or equal to 2, means V contains set of all polynomials over f of degree less than or equal to 2. Okay. V is the set of all polynomials of degree less than or equal to 2. Now, for two polynomials f1g belongs to V, we define the inner product of f of x comma g of x or f comma g as integral from -1 to 1 f of x into g of x into dx. I define the inner product as inner product of f of x comma g of x is integral from -1 to 1 f of x into g of x into dx. We need to find an orthonormal basis for V. We need to find the orthonormal basis. Now, V is the set of all polynomials. V is the vector space of all polynomials of degree less than or equal to 2 means what? What are the basis elements for V? So, any polynomial is of the form a0 plus a1x plus a2x square, because it is of degree less than or equal to 2. Therefore, what are the basis elements for V? So, we know that the basis elements are 1x x square are the basis elements for V. So, every element of V can be written using the linear combination of 1x x square. Okay. Therefore, 1x x square forms a basis of V. So, using these basis elements, we construct an orthonormal set which forms a basis of V called the orthonormal basis. So, for this, I will take up the given elements, given basis as u1 as 1, u2 as x, u3 as x square. Now, you follow the procedure as explained in Gram-Schmidt orthogonalization process. First, what we do is set w1 is equal to u1, that's equal to 1, and v1 is equal to w1 by norm of w1. Then what about norm of w1? Then norm of w1 is, you know that inner product of w1 comma w1 to the power of 1 over 2. So, now inner product of w1 comma w1 means w1 is here what? 1. So, it is 1 means it is also a polynomial, constant polynomial. So, inner product of f of x comma g of x is -1 to 1 f of x into g of x. Accordingly, what will happen? Integral from -1 to 1, w1 is 1, w1 is a 1, 1 into 1 into dx power of 1 by 2. So, if you make integration, it gives 2 power of 1 by 2 or under root 2. Therefore, v1 is what? v1 is w1 by norm of w1, w1 is 1 and the norm of w1 is root 2, therefore v1 is 1 over root 2. Okay. So, we have constructed one orthonormal vector. Set w2 is equal to s u2 minus inner product of s, inner product of what? u2 comma v1 into v1, and v2 is w2 by norm of w2 as usual. Then what will happen? w2 is u2 is x minus inner product of x comma v1 is 1 over root 2 into 1 over root 2. This is x minus 1 over root 2 is outside of the inner product. So, you write as it is 1 over root 2 into inner product of x comma root 2 is, this is like f into g. So, 1 over root 2 into x into dx. So, x minus 1 by root 2 can be taken out, 1 by 2 into the integration of x is x square by 2, upper limit is 1, lower limit is -1. So, since this is an even function, what will happen? So, this becomes 0. If you apply limits, it becomes 0 total term. Now, we have x minus 0 which is x. Therefore, w2 is x. And norm of w2 is again inner product of w2 to comma w2 whole power of that's equal to -1 to 1 x into x square dx power of. So, applying limit, you can see that the value is root of 2 by 3 or root 2 by root 3. So, norm of w2 is what? Root 2 by root 3. Therefore, v2 becomes what? v2 becomes V2 becomes W2 by norm of W2 is x by root 2 by root 3, or so root 3 by root 2 times x. Now let us take up the inner product of V1 and V2. If you take inner product of V1 comma V2 is V1 is 1 over root 2, V2 is root 3 by root 2 into x. So this is equal to minus 1 to 1 by root 2 into root 3 by root 2 into x dx. So this becomes root 3 by 2 into minus 1 to 1 x dx. So root 3 by 2 into x square by 2 minus 1 to 1 is 0, therefore it is 0 total. Means inner product of V1 comma V2 is 0, means what is say V1 and V2 are orthogonal, as well as norm of V1 is 1, norm of V2 is also 1, therefore V1 V2 is an orthonormal set. Next is set, we need 3 elements. Set W3 is equal to, okay, set W3 is equal to U3 minus inner product of U3 comma U3 comma V1 into V1 minus U3 comma V2 into V2. So this is x square minus U3 is x square, V1 is 1 by root 2 into 1 by root 2, U2 is x square, comma V2 is root 3 by root 2 into x, I written as it is. So if we integrate and apply the limits, you can see the value to be x square minus 1 by 3, means W3 is x square minus 1 by 3, and V3 is what? W3 by norm of W3. So norm of W3 I will find it out now. Norm of W3 whole square is, so x square, inner product of x square minus 1 by 3 comma x square minus 1 by 3. So if you make a calculation, so we can see that the norm of W3 whole square is found to be 8 by 45, or norm of W3 is, if you apply a root for this, it gives 2 root 2 by 3 root 5. This is norm of W3, therefore V3 becomes 3 root 5 by 2 root 2 into x square minus 1 by 3, x square minus 1 by 3. Clearly norm of W3 is 1, V3 comma, you can find out that V3 inner product of V3 comma V2 is 0 and V3 comma V1 is 0, therefore V1 V2 V3 becomes a orthonormal set. Orthonormal set, you know that every orthonormal set is linearly independent and so forms a basis, therefore V1 V2 V3 is an orthonormal basis for the given inner product space. Okay, friends and this, I will take up another example. Say, suppose V is the set of all real valued functions f y is equal to f of x satisfying the differential equation d square y by dx square plus 9y is equal to 0. Okay, here prove that V is a two-dimensional real vector space. Here we need to prove the solution set of this differential equation is a two-dimensional vector space. And also in V, if I define the inner product as u comma V is equal to integral from 0 to pi u into V into dx, then we need to show that this defines an inner product on V, and we need to find an orthonormal basis for V. So we need to show, first is this one is the two-dimensional vector space, real vector space, and we have to show this is an inner product on V, and we have to find the orthonormal basis. Okay, 3 requirements here. Okay, now first let us take up the first one, let us find out. So show that this is a two-dimensional, V is a two-dimensional real vector space. So for this, so the given differential equation is d square y by dx square plus 9y is equal to 0. Okay, so this can be written as d square plus 9 into y is equal to 0, where d is d by dx. So this can be written as d plus 3i into d minus 3i into y is equal to 0, or auxiliary equation is equal to 0. This implies d is equal to what? Plus or minus 3i. Therefore the solutions are cos 3x and sin 3x. Okay, now we know that the linear combination of any solution of a given differential equation is again a solution, because f and g are solution means alpha x is also a solution, beta g is also a solution, alpha x plus beta g is also a solution, means linear combination of any solution of a given differential equation is again a solution that you have studied in your differential equations. Therefore, we conclude that V forms a real vector space over R. Okay. Therefore, it is generated by two basis elements. One is cos 3x and sin 3x, other is sin 3x. Therefore, the basis elements, it is spanned by two elements, cos 3x and sin 3x. Therefore, the dimension of the differential equation is 2. Okay. Now, say you consider the Wronskian of these solutions. W of cos 3x sin 3x is cos 3x sin 3x, and this one differentiation. So, minus 3 sin 3x, 3 cos 3x. If you evaluate this determinant, you find that it is equal to 3, which is non-zero. Wronskian is non-zero means what you can say, these are linearly independent solutions. Cos 3x and sin 3x are two linearly independent solutions of the given differential equation 1. Okay, this is the linearly independent solution, and we know that any other solution is only just the linear combination of these two solutions. Therefore, V forms a two-dimensional vector space. Therefore, V is the solution set of this differential equation that has two-dimensional, that is a two-dimensional vector space over the field F. Or here R is the field. It's a two-dimensional real vector space. Next, second condition. What is the second condition? We need to show inner product of u comma v is equal to 0 to pi u into v into dx defines an inner product on V. Okay. So, let us take denote u as p of x polynomial solution set, u as p of x and v as q of x be the elements of V. You take any two elements. So, then what will happen? First condition of an inner product. Inner product of u comma v is what? Inner product of p of x comma q of x. But by definition of an inner product, this is 0 to pi p of x q of x dx. This can also be written as 0 to pi q of x into p of x into dx. So, this is equal to what? V comma u. Therefore, inner product of u comma v is equal to v comma u. Okay. Next is second case. Inner product of u comma u is what? 0 to pi p of x into p of x dx. 0 to pi p of x square dx is definitely p of x. If you make a square, definitely it is non-negative. So, integration of a non-negative term is non-negative. So, this is non-negative, means inner product of u comma u is non-negative, and we can show that inner product of u comma u is definitely if you assume inner product of u comma u is 0 implies u is 0. So, second condition can be proved. Third one, inner product of alpha u plus beta v comma w is inner product of alpha into u is p of x plus v is q of x plus beta times q of x. I will take w as r of x, where r of x belongs to v. Then by definition of inner product, 0 to pi alpha px plus beta q of x into r of x dx. So, this is equal to, you multiply through by r of x, it gives 0 to pi alpha into p of x into r of x dx plus 0 to pi beta times q of x into r of x dx. So, this is equal to, alpha can be taken out. So, 0 to pi p of x into r of x dx plus beta times 0 to pi q of x into r of x dx. So, this is equal to alpha into, this is nothing but inner product of p of x comma r of x plus beta times, this is inner product of q of x comma r of x. Therefore, this is equal to alpha into u comma w plus beta into v comma w. Therefore, inner product of alpha u plus beta v comma w is alpha into u comma w plus beta into v comma w. Therefore, the function which defines like this is defines an inner product on V. Inner product on V. Now, what is the final step? In the final step, we find the orthonormal basis for V. Okay. Now, we know that cos 3x and sin 3x are the solutions or basis elements for V. Therefore, I call it u1 by cos 3x and u2 by sin 3x. Now, we construct the orthonormal basis using these basis elements u1 and u2. So, the same procedure. Okay. Set w1 is equal to u1, that's equal to cos 3x, and v1 is equal to w1 by norm of w1. Then norm of w1 whole square is w1 comma w1. So that will be equal to inner product of cos 3x cos 3x. So inner 0 to pi cos square 3x. So cos square x can be written as 1 plus cos 2x by 2. Therefore here cos square 3x means 0 to pi 1 plus cos 6x by 2 into dx. So if we integrate this, 1 by 2 can be taken out. So integration of x, 1 is x plus integration of cos 6x is sin 6x by 6. So 0 to pi, if you apply the limit, it can be found to be 1 by 2 times pi. So norm of W1 square is pi by 2. Therefore norm of W1 is what? Root pi by root 2. Root pi by, this is root pi by, norm of W1 is root pi by root 2. Therefore V1 is W1 by norm of W1, that is equal to root 2 reverse. 1 by norm of W1 is there. So root 2 by root pi into cos 3x. This is V1. Again set W2 is equal to U2 minus inner product of U2 comma V1 into V1. So U2 is sin 3x minus U2 is sin 3x comma V1, just now we have find out root 2 by root pi into cos 3x, root 2 by root pi into cos 3x. So this is equal to sin 3x minus root 2 by root pi cos 3x, you write as it is because it is outside of the inner product. So this is equal to, if we apply inner product for this, 0 to pi root 2 by root pi into sin 3x into cos 3x into dx. So this is sin 3x minus 2 by, so root 2 by root pi can be taken out. This becomes 2 by pi into cos 3x into 0 to pi, integration from 0 to pi. This is like 2 sin x cos x is sin 2x. So according to this,